always make the probability of at least 1 minus the probability of none. I can always do that. And it almost always makes it quicker because there's one calculation here. Here there would be many, many calculations. This would so suck to do this directly. At least one, what does it say for the one I'm looking at? At least one unemployed means the first one could be unemployed. Or the second one could be unemployed. Or, and then I got to do, or 2 of them are unemployed. Or the middle 2 are, holy crap. Or 3 of them were unemployed. Or all 4, holy shit. Calculation, calculation, calculation. Oh crap. 1 minus none. 1 calculation subtracted from 1. Done. Right? Okay, maybe. I'm always so hopeful. Okay. All right. So any questions from homework or anything left undone before we continue with chapter 5? Yeah.
Number 26 on 5.2 D.
Oh, good. I love it. That's the one I wanted to do before I move on. So, perfect question. Oh, Hall's cough drop. Why do you mock me? You asshole. Okay. Sorry. It's almost gone. All right. So 26. And this is really, this is the crux of what this is used for, the idea in section 5.2. So real quick question, car insurance. Who in here is 24, almost 25? Anybody? I'm pretty sure it's true in California. I didn't turn 25 in California, but when you turn 25, do you know what happens with your car insurance?
It goes down.
Yes. So when I got my first bill, my first car insurance bill after I turned 25, I was like, wow, that's freaking awesome, right? What's that got to do with? Why the hell is that true?
Risk.
The risk has gone down that you're going to have an accident. It doesn't mean the morning you wake up, you're 25, you go, that's how you drive. Right? So they took into account the probabilities that different age groups have accidents, and of course the ones that have a higher risk, they're going to make them pay more. So really what that has to do with is if you made a chart like this for how much, as an insurance company, how much you expect to pay out, and the probabilities of that bad of an accident, multiply, cross, add down, that's the average amount you're going to have to pay out, so you're going to make everybody pay that much to cover it, at least. You actually make them pay a little more, so you end up making some money, right? So when you have a different age group, these probabilities go down. The probability of 0 money being paid out goes up, so you're able to charge them less. I don't know if you guys are kind of with me. So this problem is actually not exactly like that, but this is sort of like that. Number 20, which one? 26?
Yes.
Number 26 says, in New Jersey's? Yeah. Pick 4 lottery game, you pay 50 cents to select 4 digits, such as 1332. If you select the same sequence of 4 digits that are drawn, you win and collect $27.88. $2,788. If you lose, you collect 0. Right? So the idea is really try to create this table out of what they tell me. Now the first step is, okay, there's 4 digits. The first step is to fill out what this is. How many different things could happen here? 2 main things, right? You could win or you could lose. That's easy enough. Sometimes it'll be different. Sometimes there's like 3 prizes, so you can win the grand prize, or win the next prize, or win the next prize, or lose. So there might be more entries here. Now, what number goes here? If you win, how much money do you actually make?
$27.87.
I like it. Not $27.88, right? Because to get into the game, you had to lose 50 cents to begin with. So how much money do you make when you win?
27, 87, 50.
I love it. You guys see where I got that from? If I win, what's the value associated with that? This number. So if I lose,
Negative 50 cents.
beautiful, you're out the 50 cents. Or in dollars, negative 0.50. You got to put that negative in there to show which direction the cash is going. Here it's going towards me, here it's going away from me. Damn. Now you got to put the probabilities associated with each. If there's only one 4-digit number that wins, what's the probability I get that one 4-digit number? How many 4-digit numbers are there?
1 in 10,000.
10.
Okay, well, here's a 4-digit number. How many numbers could the first number be? 10. Could be 0, blah, 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 right? How many numbers could the next number be? 10. So for each of these 10, there's 10 that could be next. So far, I've got how many numbers? 100. 10, and for each of those, there's 10. So can you imagine? I don't want to make the tree for this. There's 10, 1, 2, 3, 4, and then coming off here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 times 10 is 100. The next number, there could be 10 digits, and the next number there could be 10 digits. So what's 10 times 10 times 10 times 10?
10,000.
10,000. So there are 10,000 possible numbers. What's the probability the one you pick is right?
0.0001.
Well, how'd you get there? Set it up for me first. I like it.
1 out of 10.
1 out of 10,000. 1 out of 10,000 probability you win. So what's the probability you lose?
9,000.
9,999 out of 10,000. That sounds about right. So 1 out of 10,000 chance you'll win. The probability of this is this. The probability of this is the larger one, 9,999 out of 10,000. So a lot of problems. If you can put it in this format, situation probability, situation probability, situation probability. How do you find the average? You multiply, add, right? Just like we did last time. X times P of X, and then you add those up. So if you can put it in this format, it's easy. You multiply probability times value, and then you add all those up. That's what we did last time. So now just do this times this, plus this times this. What do you think this should come out to be? Should it come out to be a positive number or a negative number?
Negative.
Yeah. Or else the lottery people are stupid. They want money to be going away from you on average, right? This is very interesting, though. Is everybody doing this for me? X times P of X, right? Because the mean is the sum X P of X. So if you do this times divided by 10,000 minus 0.5 times 9999 divided by 10,000, what do you get?
For the mean.
Something or other. So here you get 2787.50 divided by 10,000. And here you get half of 9999 is 4999.5 if I in the negative. So when you add this up, yeah, you get negative 0.2212. So about 22 cents lost. So every time somebody plays, they lose an average of 22 cents, which is kind of interesting to think about that. So if 1,000 people play, how much money can the lottery expect to bring in for the state? If 1,000 people play,
$2,200.
well, 2,200 cents, right? So 22 bucks. Do you guys kind of see what I'm saying? Every time you play this game, over the long run, you'll average a loss of 22 cents. Because you'll have to play it so many damn times before you win that when you couple that with how much money you paid so far, it's going to come out to a loss. On average. That's the whole idea. It's on average. So does this kind of make sense to do then? If you're almost guaranteed to lose money in the long run? No. But still we do it, especially if we don't pay that much money into it, right? We still do it. What the hell? Lightning strikes. You never know where. So in a casino, every single game in a casino has what value here? When you finish, yeah, it's got to be negative. So they don't care that the guy over there just won $5 million. They got 5 million people losing $2 right then. So they're still up $5 million. Who cares? They love it. There's the guy. Oh, $5 million. Everybody, oh wow, this going here, this big, you know. And the casino guy's like, yes, we make some of you rich, and the rest of you make us rich. It's like, holy shit. All right, so that's the idea there. And I don't think I've said this word yet, but you see this in the book. This is also called expected value. And the mean is very often the most likely thing to happen. That's why it's the expected value. It's what I expect to win or lose over the long run in this case. Really cool thing about that, what's the first 3 letters here kind of? EXP, expected value. Yeah, that's crazy. Okay, always hopeful. So there's one in there about, I can't remember if I assigned the one that was the life insurance problem. I did another one after that, number 26, but that's one immediate use of this probability distribution, right? Doing something like this. Assessing risk. Has anybody ever seen that movie, Along Came Polly? Yeah. Ben Stiller, yeah? The scene I always remember is him dancing. But he did that risk assessment. So this is sort of like risk assessment. If somebody says, hey, you've got $10,000 to invest, there's this chance that we'll fail, and there's this chance that we'll succeed, and if you succeed, you get $80,000. You can make a risk assessment. You can do, okay, $10,000 I got to pay in, and I lose that if it doesn't work, but I gain $80,000 if it does work, and then you can just multiply the probabilities and see. If it comes out positive, do it. Over the long run, you will be ahead if you do things like that. Comes out negative, maybe don't do it. Over the long run, you go behind. If any of you play poker at all seriously, anybody play poker semi-seriously? Pot odds, risk assessment, isn't that everything involved there? Yeah. What have I put in so far? How many outs do I have? What's the situation? Do I want to put more money in or not? It's all based on stuff like this, expected value, right? You do the things that over the long run would get you ahead. Sometimes they're all probabilities, so you can still lose, but it's the right way to go in the long run. Okay. Cool. Any other questions from? Oh, more cool. Okay. All right. So we're actually going to get into section 5.3. And if you missed the last couple days or you didn't get it, come up to me at the end of class. I got a handout that goes with section 5.2. If you didn't get that handout. Bless you. Some of you guys might realize we're getting ever closer to what I keep calling the most important chapter in the book. It's coming up pretty quickly. And that's where we're going to be using z-scores almost exclusively for things after that, once we get into chapter 6. This is one of my favorite things, are binomial probabilities, because so many things line up like this. Binomial. Who remembers that from algebra, what that meant? 2 terms, right? So in this case, in statistics, it means 2 possible outcomes. So if I roll a die, would that be considered binomial? Mm-hmm. Why not?
Just
How can I make it binomial, though? I can make anything binomial.
Roll 2 dice.
I can say I roll a 5 or I don't roll a 5. There you go, 2 outcomes. Do you see what I'm saying? And that's not cheating. That's if I'm looking for 5s, then what am I not looking for? Not 5. So it kind of automatically puts itself into 2 categories, right? Either it's this or it's not that. So there are a lot of things I can look at using what we're about to talk about. And we've already done a few things, to tell you honestly. So to get into this, let's say it is known that 40% of Californians are Democrats. I can't remember exactly what it is, but we'll go with that. So the probability of D is,
60%.
careful,
40.
straight up at 40%. What's the probability of not D?
60.
60%. Okay, cool. So let me do something to help myself out and also to get us going towards the notation we're going to use. There's always going to be a this thing and a not this thing for binomial. Are we all cool with that? Right? Snow or not snow, Democrat, not Democrat, whatever. So let me call this thing, let me call it P. So this is going to be the probability of success. If I'm looking for Democrats, when I find a Democrat, that's a success. A success does not have to be a good thing. I could be looking for dead bodies out in some field somewhere. So if I find a dead body, that's a success. Doesn't have to be a happy thing. It's just what I'm looking for. Cool? So what do you think I'm going to call this one, maybe?
Probability of failure.
Yeah, probability of failure. F would sort of make sense. We're going to say Q. It's not my choice, but hey, too bad for us. So these are the symbols they decided to use. It's sort of like X and Y for algebra. The P and Q is the probabilities for binomial situation. Let me just take you over here. Okay. So now, how are we doing so far? So when I put a little P down, what does that mean I found?
What you're looking for.
A success, which in this case is a Democrat. Cool. And if I put a little Q down, that means I found somebody's not a Democrat, right? So let's say I pick 5 people. What's the probability I get exactly 1 Democrat? Now this is different from the ones I've asked before. If I said the probability the first one's a Democrat and the last 4 were not Democrats, that would be pretty simple, right? In fact, let me put this here. If I said probably first Democrat, last 4 not Democrat, how would that look?
0.4 times 0.6 to the third.
Yeah, 0.4 for the first to be a Democrat, and then 0.6 4 more times, right? So it'd be 0.4 times 0.6 to the 4th. And look at this. Why does this make sense? How many Democrats are in this equation? 1. How many not Democrats are in this equation? 4 of them, right? The difference is, how many ways? Is that the only way to get 1 Democrat to get them on the first go?
No.
So we could do that this way, get it right off the bat, and then the other ones have to be Q's, right?
Mm-hmm.
Or, so I could get a Democrat and not, and not, and not, and not. Or what else could I do to get 1 Democrat? I could pick him or her second. I think we get the idea here, maybe. Or third. Thank God I didn't say I picked 80 people. Or fourth. Or last. Right? Yes, sir.
But aren't you saying only the first one has to be Democrat over there, or it's just?
It's just an exact one.
This was just a recall. So the actual question I've got right now is this.
Oh, exactly.
Probability of exactly 1 Democrat. I'm not saying the first one has to be Democrat.
Okay.
I just want 1 Democrat. How are we doing so far? So sort of like, remember when we did the birthday thing? And if I said, do you think somebody in here has the same birthday as me? You guys say, probably not. I'll put money that nobody does. Because there's a good chance that nobody does. But the minute I said, what's probably that 2 people in here have the same birthday, there's a lot more possibilities then. They could have the same birthday as you, or you, or you, or see, now there's a lot more possibilities. Here, very restrictive. The first one has to be a Democrat, the other 4 don't. Here, exactly 1 Democrat. There's a lot of ways to do that. It's going to be a higher probability because there's more ways to do it. Yes, sir.
So would you just take the probability and do that as you would if you would recall, but then just do it to the 5th, since it's the same probability
Well,
each time?
or means what? Add. So here in this one, this is Democrat first and not Democrat second and not Democrat third, so forth. That's why I'm multiplying here, right? Or I could do it this way. So I add. Let's do a little algebra here. Remember, I told you there's very little algebra in statistics. Every single one of these looks like what? What's a better way to write P, Q, 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 Q? PQ to the fourth. And we already know that kind of from this. They all look like PQ to the fourth. How many of them are there? Careful.
Times 5.
So what's PQ to the fourth plus PQ to the fourth plus PQ to the fourth plus PQ to the fourth? What is that?
PQ to the 4 times 5.
5 PQ to 4s, right? You get 5 of these. Now that level of algebra should be something that we can all handle, right? It's adding like terms, not a big deal. This is awesome because it's very simple, right? When I ask a specific example, you only did one of them, of course, right? That only represented one way to do it. When I say exactly one Democrat, well, there's 5 ways to do that out of 5 people. Now, let's figure out what that is. 5 times what goes in for P? 0.4 and 0.6 to the 4th. Let's see what that is. I have no idea. 0.2592? Is that what you guys are getting?
Yes.
Sweet. Yes.
Yeah, I'm still confused. So this answer for the first part or the second part?
The first part.
Oh,
Exactly what I don't know why I drew it line there. So exactly one Democrat. Because how many ways is there to get exactly one Democrat? 5 different ways. Cool. This problem here is done at this point. Just plug that in the calculator. It's done. Yeah. So thank God there's a general formula that helps me out here. Because can you imagine, what if I just do this? Still pick 5 people. We're still talking about Democrats and not Democrats, right? We still have the same situation. P is 0.4, Q is 0.6. But now I want the probability that I get exactly 2 Democrats. Can you imagine trying to make that list now? What's going to be difficult about making that list? Imagine it. A lot more options, then I'm going to get confused. Did I already do that one? Did I get every one of them? Shit. There's a way to do it, but I don't want to do it. Can you imagine if I picked 80 people? What's the probability that I get 22 Democrats? Well, the first 22 could be Democrats. Or the last 22. Maybe the first 2 and the last 20. Maybe the middle 7 and, oh, shit. Right? But what I really want you to realize, so I don't know what the number, I don't know how long the list will be. Like right here, this 5, why was there a 5 here? It's how long the list is. This list was easy. I can see it. I can count it. I don't know in this case what that number is going to be. But what's this going to look like? Q to the what? Q to the what?
P squared, Q to the third.
Because I want 2 Democrats, so P squared, and the rest are not Democrats. What number goes there? 3. That part of the equation is easy. I'm going to show you right now how to get this part of the equation. And we're going to do it a little bit differently than the book, so I want to make a big point out of that. And this is where you're going to need, oh crap, bring him back to life. There his note is. It's not. So if you got your calculators, go ahead and bring them out. If you don't have one, there's some on the table up here still. See this one actually. Doing what you're supposed to do now. I love it. So just make sure everybody's, I hope to God you guys are all exactly 2 Democrats. The easiest way to do that would be what? The first 2 are Democrats, and the last 3 are not. And then maybe I let 1 P drift through. Do you see that? But can you imagine just trying to keep track of that? Maybe both of them drift through, or maybe, and then maybe this one's here and then the other one drifts around. I mean, good God, there's a lot of different ways to do this, right? But every single one of them has p squared, q cubed. P squared, q cubed. And what's awesome about it, 2 Democrats, the rest not Democrats. You can always do that. Kicks ass. So what we use here, and this is that section 4.6 that I skipped, there's really only one piece of 4.6 that's important for statistics, really. And that is counting the number of ways to choose something. In fact, the really cool thing is it's exactly the word to use, choose. So how many things do I have total? 5 people. So I got 5 people. I want to choose 2 of them to be something, right? So what's one way to do it? This way. What's another way? This way. So the cool thing is this is exactly what it looks like in the calculator. 5, choose 2 of them to do something. So if I would have said 70 people, and I want 38 Democrats, what would that have looked like? It would have looked like 70 choose 38. Let's go further. P to the 38. I want 38 Democrats. Q to the what?
62.
It's got to add up to be what? Not 100. 70. I got 70 people, right? So 38 of them are Democrats. 32 of them must be not Democrats. You see how I'm covering my ass right now? It's binomial, so I don't have to worry about, what about the independents? We're there with the not Democrats. Leave me alone. They're all there, right? I'm not leaving anybody out. Cool. All right, so here's how you do this in the calculator. So look at this whole, what would this whole equation look like? The probability of 2, 5 choose 2, 0.4 to the second. So I got 5 people, choose 2 of them to be Democrats. So I have 2 Democrats, the rest 3 are not Democrats. Isn't that how the whole formula would look? I love that you can just see it. This piece just tells me how many ways there is to do it. 2 of these, the rest are these. This formula is awesome. It sets itself up. I know right now many of you are still confused, but once you do a few examples, I'm hoping you'll see how it kind of sets itself up. So let me talk about how to put it in the calculator right now. So everybody do this with me. So I got 5 people. Go to math. Now where in here do you think I want to go? Yeah, PRB, probability. Math, go to probability. Number 3 is choose. Do you see how it's got 5, choose something, right? So 5, and then hit, either scroll down to 3 or hit the number 3. 5, choose 2. Trying to think about, let's just put the whole formula in. You ready? Times 0.4 to the second, because I want 2 Democrats, times the other guys to the third, because I need 5 people total. That's kind of nifty. 3, 4, 5, 6. I wish I could say I did that on purpose, but no. So about a 34.5% chance that we'll get exactly 2 Democrats from here. Yes.
Can you just repeat that one more time?
Sure.
Thanks.
So 5, and this is all in your calculator Bible too. There's like a whole binomial section. I think it's on the back of your calculator Bible.
How do you end up
I'll show you right now. 5, math, PRB. See at the end there, so you just have to arrow over to it. So go to math, and then you hit over. You see that? Cool.
Okay.
So it's the last option, number 3. So 5, choose 2 people times 0.4 to the second times 0.6 to the third. Now real quick, what 5 choose 2 by itself? 5 choose 2 is 10. What does that tell me again? What's that 10 tell me?
There's 10 lists.
There's 10 ways, right? So if I listed this whole thing, I'd get 10. If you try to do this by hand, you almost will definitely come out with 8 or 9 or even 12. You'll either leave something out or double count something. What about this one? Let's do this one. If I got 70 people, it's probably 38 of them are Democrats. So let's see what that whole formula looks like. Pick 70 people. What's the probability that 38 are Democrats? So how does that formula set itself up? I've got how many people?
70.
70. And I want to choose how many to do something specific.
38.
I want to choose 38 of them to be this. So how many of these do I have?
38.
38. They're kind of repetitive, which is nice. 70 people. Choose 38 of them to be successes. So I got 38 of these. And, yeah, oops, 32 of these. Cool. So real quick, you guys notice what does this number plus this number always have to be? 70, right? What letter do you think 70 is? What symbol would we use for that? N. It's my sample size. This is N. Okay. So how do we put this in the calculator? I would put 70, math, PRV, number 3. Not sure this can even handle it, so let's find out. 38. So 70, choose 38 times 0.4 to the 38. I want 38 of those guys times 0.6 to the rest. 32. Thank God. All right. This calculator can only handle up to so much digits out. So sometimes you'll do these and it might say overflow error or something like that. Thankfully, none of the ones in the book should do that to you. Yeah.
How you get a 10-way? I don't know how to get a 10-way for that
Oh,
number.
the 10?
Yes.
So real quick, for this one, let's do 70, choose 38 by itself. 70, math, go to PRV for probability, choose 38. How long would this list be? Right? Take a guess. Some of you guys already have the number on you, so don't take a guess. Those of you who haven't done this yet, take a guess. I mean, choosing 2 from 5 was 10 big. How big of a list do you think it would be for choosing 38? So maybe the first 38, or the last 38, or the middle 2 and the first 18 and the last 18. It's going to be stupid big. Bigger than you think. It'll be that big. 8.7 times 10 to the 19th. So you move that decimal over 19 freaking times. That's huge. What's kind of weird about that? That's what that is, right? That is this. So how did I end up with such a small number? Because 0.4 to the 38 times 0.6 to the 37 is stupid small. So you have stupid big times stupid small, kind of averages each other out. It's always going to come between 0 and 1, of course, right? That's why I say put it all in at once. Because sometimes this piece will be too big, but all at once, you can handle it. Trust me, it's a little weird, but it actually does that. So get used to putting it all in at once. All right, let me do a problem fresh. Let's just do a brand new problem and see what you guys can do with it. Oh, and real quick, before I give you a problem, let's talk about what this formula looks like. So if I have n things, and P is success probability, and Q is failure probability. And I want the probability of X successes. This is what we've been doing, right? I give you a total number of things, like 70 people or 5 people. Success, failure, and then the probability of a certain number of successes, right? That's what we've been doing. This would be n things, choose how many? X. That's how many successes I want, right? So P to the what power? How many successes? X. I love it. Now here's where the weird part comes in. Q to the what power? What's left? N minus X, right? Because when it was 70 and 38, I had to subtract them to see what was left. That is your general binomial probability formula. Again, this sort of gets in our way. People get a little freaked out about this. But the actual setup is pretty simple. It's very straightforward. So here's a problem. Let's do this. It is known that 83% of Americans like mint chocolate ice cream. Anybody not like that? Anybody not like mint chocolate ice cream? I'll eat yours. All right, cool. I got you covered. It is known that 83% of Americans like mint chocolate ice cream. Right? Hopefully you guys all are cool with the fact that I just totally made that up. It's not what we normally do, but I won't. If we select, let's say 62 Americans, what's the probability that exactly, what, Jeff? I don't know, exactly 50 of them like it? So try to set that one up. Try to set the formula up, and then if you have any trouble putting in the calculator, call me over. And this is, I'll give you a little hint. The minute you see one of these problems coming at you, and these are pretty obvious to tell. There's a probability of this, so there's a probability of not that. I took a total number of people, I'm asking what's probably of this smaller group of people, right? So I can summarize for myself everything I need. So I would highly suggest you first summarize what N, P, and Q are. Yep.
So every time you see the word exactly, you think about this?
Not necessarily, but it's because it's a binomial situation, right? There's only two possible outcomes. There's a success and a failure. There's an N and an X, right? It kind of jumps at you that it's a binomial.
I think we've done like two probabilities before, and we did not use this thing, right?
Oh yeah, we've done this kind of thing before because I was more specific, right? If I said what's the probability the first three don't like it, but the last 59 do, that would just be 0.83 to the 59, 0.17 to the third. Directly, right? There's not more than one way to do that. I've told you exactly the one way I want you to do it. Whereas when I say exactly 50 of them like, well, it could be the first 50, or the last 50, or the middle 25, or the first 10, last 15. Holy crap, right? That's why we need this formula to help us out now. Question? Just make sure everybody's on the right track. I should just put you here in general. Good idea. So somebody have what that formula looks like?
62C.
Good. We got 62 people.
Choose 50.
Choose 50 of them to do something.
Times like 83, 50.
So I want those 50 to do this, to like it. And how many do I want to not like it? And not like, of course, has to be the other 17%.
Like 17 over 12.
Good. The rest of them don't like it. So do you guys, I think most of you guys maybe are seeing how these formulas set themselves up. This is awesome. Doesn't normally happen this way. Now it's all about how to get that into the calculator, right? So 62 math probability choose 50 people. So I want how many 83%? I want 50 of them. And the rest are 17%. And that's 12 of them. Cool. All right, 0.1132 roughly. Just over 11% chance, right? Okay.
I'm still confused on like the 50. Why you put 50 on like after C and then 50 up top? Like I'm still confused on that.
Like here, and then up here.
Mm-hmm.
Because this piece just tells me how many ways there is to choose this many people, right? Because it could be the first 50 people or the last 50 people or so forth. So 62 people, I want to choose 50 of them to do something. So how many do I want to like it? Well, 50 of them. So the formula is a little repetitive, but that's kind of nice. Whatever number is there is going to go there.
Okay.
And then how many do I want to not like it? Well, the rest.
Yeah.
Must be 12 of them because I've already used 50 of them to like it. Cool. Yes, ma'am.
So do you want us to go out 4 places after the decimal?
Yeah, I'm going to move us in the direction of doing 4 places because we'll actually, in chapter 6, we'll see there's a chart that all the probabilities go out to 4 places. Yeah. Yes?
My question is, how are you getting the 62 and CR? Because I'm still getting 5.
Oh. You're still getting 5.
And that's why it's coming up with 0.
Oh, let's put 62. And choose. Right.
So I have to put the number first and then do the 5 math.
Yes, and then do the math. No 5, right? So do 62, math, probability, choose 50. So there's no 5 in the middle there. Yeah, cool.
Okay.
The 5 was just because I think earlier we had 5 total people. Now I've got 62 total people.
Okay.
Cool. Any other questions right now? Okay. Let me see. Now, real quick. What would kind of suck here, and this is sort of looking ahead, what really makes this kind of thing useful is if I said the probability of at least 50 of them like mint chocolate ice cream, because maybe I've only got enough for 50 people. So I want to know the probability that there are going to be people that are upset at me, right? So I put together this party, 60 people will come, and I'm like, oh shit, I forgot to ask them what kind of ice cream. I've only got enough mint ice cream for 50 of them. What's the probability that at least 50 of them would want mint ice cream? And then I can see what's probably I'm going to be in trouble. Something a little less silly than that. Airlines. I'm sure you all know that they always overbook flights because there's a certain probability that somebody won't show up. So they always try to overbook it just enough so that they'll have more filled flights, but a small probability that they'll have somebody get bumped. Now recently I think bumpage has gone up. I don't know. The last few times I've flown, one time I got bumped. Another time a lot of people got bumped. You guys know what I'm talking about? Anybody? Okay, good. So most of us have flown somewhere. This kind of thing would be perfect for that. If the probability that I've got 400 people booked on a plane, what's the probability that 10 of them won't show up? Right now, if I've overbooked it by 10, then I'm hoping that probability is kind of high. That at least 10 won't show up because I don't want to have people upset at me. At the same time, I want a full plane, right, to make it more efficient. Okay, maybe. So that's exactly the kind of problem this is beautiful for. Very real life, real world problem.
So what would be the difference if it was at least 50?
Well, okay, the difference here would be, what do you guys think? At least 50 means what?
50 or
It could be 50. And we did that probability, right? Or 51, I'd have to do that probability. Or 52, I'd have to do that probability. Or 53, that probability. Shit. Do you guys see what I'm saying? So thankfully in chapter 6 we're going to learn something that makes a shortcut of this. Otherwise I've got to do this formula.
Oh, so we're not going to see that yet?
No. But that's the kind of problem that makes chapter 6 make even more sense. It's like, it helps me do this kind of problem quicker. Because it's not always going to be exactly. Sometimes it's going to be at least, at most. Which means I have to do this formula more than once. Sometimes 20, 30, 800 times. No, really, I don't want to. And I'm not going to make you do that. Don't freak out. Right? Okay. Let me see. Let me ask you this. So coming off the same problem here, right? Coming off that same exact problem. What do you think is the expected value? What do you think is the average number of people who like mint ice cream? Mint chocolate chip ice cream. Out of 62. And this is a much easier question than you might be thinking in your head. Let me ask you a related question that's actually easier. I used to always pick on Shaquille O'Neal because I actually hate the Lakers. So he'll always be like, even though he came to my Celtics, he's still sort of always a Laker first. Let's say he makes 30% of his free throws, to be generous. If he takes 10 of them, if he takes 10 free throws, how many would you expect him to make?
3.
What'd you just do?
10 times
10 times 0.3. You took 30% of 10. If he took 20, how many would you expect him to make?
6.
30% of 20 is 6, right? So you always do the percentage times the number. So the average, the expected value, the average will be NP. Always, which really only makes sense. If 83% of people like mint chocolate ice cream, and we have 62 of them, how many on average will like it? 83% is 62. And what is that?
51.5.
Sorry, say?
51.5.
51 and a half. Cool, right? Okay.
But since it's people, do you need to round down?
No, an average is fine. There was a problem way earlier about 2.5 kids, and is this a problem? No, it's an average, right? If I had 100 times as many people, I'd want to say 5150. I don't want to say 5100. That'd be way off then. So decimals are perfectly fine for averages. I know we can't have half a person, but it's an average. It doesn't have to be a whole number of people. It's an average. It could be a decimal. Cool. Okay. So in this case, do you see why I picked the number 50? I wanted to make sure the probability came out to something not 1.0 times 10 to the negative 18th. So I took something that was close to the average. So what should be the most likely number of people then? Did it come out to be exactly 51.5? No.
51.46.
46 or 4 something? So what's that closest to? What whole number is that closest to?
50.
Okay, so I sort of gave it away, but what's the most likely? Which number would have the highest probability? What number of people would have the highest probability? What's another name for the average? Expected value. So what would you expect to happen? 51. That's what that closest to, right? So what should have the highest probability? If you expect it to happen, it should have the highest probability, right? So do this again. What would it be if it was probability of 51? It'd be 62 choose 51. 0.83 to the 51, and then the rest have to be 17%, and that would be 11. Cool. So watch, here's something kind of cool. Watch this, watch it. If you hit second, enter. Trust me, you're going to love that. See how it just brings up the whole last thing? And now I can go up and just edit this, make that 51. Make that 51 and make this, no, Jeff. Good job. Make that 51. And then make this 11. Oh, if you have a normal calculator, it might be easier, but oh.
If we're 120.
I know, thanks. There you go. And how does that relate? That's 13%. How does that relate to the one we just found? It's higher. And if I did 52, it would be a little lower. If I did any other number, it would be definitely lower because 51 is the most likely thing. Whew. All right, last idea, and then I will release you. Last idea. So we know how to calculate the average for a binomial situation now. What else do I need to know how to calculate? Standard deviation, right? So this is the point I made last time. When we got to the x, p of x, I want to be able to find two things for sure. The mean and the standard deviation. Because then I can answer all these questions about 68% within here and so forth, right? I want to be able to find those two numbers. So for this, I want to do the same thing. So for a binomial situation, the mean we know is NP. And I can explain that using Porsche-Keeler-O'Neill. I'll explain why that's true. And you just did it without even knowing anything about what it should be. You just did it correctly. This is the one that makes a little less sense. The variance is NPQ. So what's the standard deviation? Square root of NPQ. So there's two of the best formulas so far. You guys agree with me? For finding the mean and standard deviation, those are the two easiest formulas we've seen yet. So here's one little situation, and this will be it. Let's say, I don't know, 12% of Americans file their taxes late. Okay? If we pick 386 Americans, what's the average and the standard deviation of the number filing late? What's the average number I'd expect to see file late, and what's the standard deviation of the who I'd expect to see to file late? I just lied a little bit too. I'm going to do one more example after this. You guys should be used to that with this. Math teachers. So how do I set up the mean then? What would it be? 386 times 0.12. So whatever the hell that is. 46? 46.32. So if I had to take a guess, 386 Americans, I would guess that about 46 would file late, right? But of course, will it always be 46 filing late? Exactly? No, it's going to be give or take some amount. So standard deviation kind of tells me how much I expect it to be off by, possibly. So what's the standard deviation going to be? It's going to be square root of NPQ. So square root of 386 times 0.12 times what? What's Q? Beautiful. 1 minus P, right? Always the rest. 0.88. Six point 6.38. Damn, I was close. What is it now? 6.338. 4. Where's the 5? Okay. Remember now, you know this about me. I'm a little bit picky about that. At least 3 places on the standard deviation. I don't care what situation it is. Okay. Actually, we'll make this the last one. So don't freak out. What's my minimum and maximum then that I would expect? How far out do I have to go to hit unusual? How far away does it have to be? 2 standard deviations, right? 2 standard deviations. That's why 5% is unusual, because how much of the data is outside of 2%? 2 standard deviations for a normal. 5%. See, they go hand in hand. So if I have 46.32 in the middle, 2 standard deviations down would be subtract 2 of these, right? Minus 2 times 6.385, whatever the hell that is. And 2 standard deviations up would be plus 2 times 6.385. This would be the minimum, and this would be the maximum that I would expect. Anything outside of that range would be unusual. I love it. That's exactly the kind of homework you'll see in that section. And by the way, we just did section 5.4 also, right? 5.4 is all about this here. So you'll see this. You'll say calculate the mean, calculate the standard deviation. Is 117 unusual? Well, you figure out what the boundaries are, and you can see, is it unusual or not? Is it in there or not? Cool. All right, guys. Don't forget about your project. Came in late, you might want to come up and see me. Oh, yeah. Oh, cool. Thank you. Okay. Oh, yeah.
I just want to make sure that you have it.
Oh, yeah.
All right, cool. I don't care to get back anytime soon. I just want to make sure that you
Good.
get lost.
Thank God for that. Oh, this one. Oh, which one? Yeah, this one. I sort of already did the work in the back, though. Oh, and you need one too. Oh, crap.
Yeah, I'm coming.
Oh, that was from a while back. The other one, it's got the XP of X tables on it, and the talking about how to do it in the calculator. That handout. Oh, good. So you need yours for that. So I think you just ran out of that one. I thought you had more than that.
Is that the one from last week?
Yeah. So if you email me, I can email it to you. So it's the one that talks about section 5 too. With the XP of X, and it tells you how to do it in the calculator.
Yeah.
Yeah. You email me, I can send it to you.
We're turning that in.
No. That's just the explanation.
Is that all that you lost?
Yeah, just like
I can.
yeah.
So the other one 5.2,
Okay.
that is what I'm.
Okay, I understand.
What's up? Sorry, are you asking me? Or?
Yeah.
Okay. What's up?
5.2, I just have to email you. Or-
Yes, that's that handout. Yeah,
Okay.
sure.
And then you said the project.
Oh, that's this one.
Oh, this is our project.
So read through that. Let me know if anything doesn't make sense. It's due next Tuesday. Like I said, there's actually an extra credit to this.
Yeah. To go to the meeting. They're like hosting.
No. Yeah. I'm just helping out with hiring you guys as consultants to do the analysis.
Oh,
Yeah.
okay. So.
And you get paid nothing.
Alright, so.
So just let me know if something on there doesn't make sense.
Alright, you're taking an email today.
Oh yeah, all the time.
For this one,
Oh, just you put it like that.
oh, okay.
So it's like 10 to negative 4. I didn't take the points off because that's true. I just want to make sure you know what that means.
Okay.
Yeah. Oh, because this is the